There's been obviously a lot of noise about the metaverse recently. Facebook, of course, changed their name to Meta. It's been very subject of a lot of talk in the investment community. But what does it really mean? It goes back to 1992, the word itself, to Neil Stephenson's book Snow Crash, where he envisioned a large shared virtual world where people interact in real time. And it's a compelling notion, right? I mean, why should we continue to interact with each other in a two-dimensional web when the technology is now available to interact in 3D? What can we do to make this, to turn this into not only a reality, but a non-dystopian reality, not what maybe you see in Ready Player One, but something that's actually genuinely useful, enriches our world, and solves practical problems. Well, whoops, it's no longer, this isn't advancing. Let's see. We got a little problem here with advancing the slides.
These things are never easy for some reason. Okay.
Use the clicker. Yeah, use the clicker. No.
Why does it?
Oh, here it goes. Now it's working. Okay, there we go. Perfect.
Okay, I don't know how to get rid of this top part though.
That's okay.
That's not going to mess up here.
Okay. All right. So first point I want to make is that the metaverse, in our view, is something much more than social. I mean, social is what you probably hear people talking about most of the time, but we see it as the way that 3D environments are shared for a lot of practical purposes. One of the big ones is architecture, engineering, design, construction. You obviously want to make sure you're building the right thing. How do you do that? You want to simulate it before you build it. All the participants in the simulation need to be on the same page. How do we do that? By sharing these three-dimensional data representations in whatever the smoothest way is possible. We want to obviously create this sharing of 3D worlds in media and entertainment. Arguably, that's already happening in a lot of game worlds. Product design and manufacturing is another place where this is extremely valuable. We want people, not only in the design and manufacturing, but also in the marketing, to be able to share the same representations to seamlessly communicate with each other. Scientific visualization, you do great science, you want people to be able to see it. We do these very elaborate simulations. Those need to participate with all the other communication that we do. It all needs to be connected together. And finally, this is a subject that's dear to NVIDIA's heart. We're going to be building all kinds of artificial intelligence tools. And these tools need to be trained. You need to have experience in some kind of world. What world is that going to be? That world will be built in the same technology that builds the metaverse. These artificial intelligence actors are going to grow up in virtual worlds. Now, in the popular imagination and science fiction, it's all something where we strap ourselves into these weird devices, and we see the metaverse a bit differently. That it's about sharing these 3D models, 3D environments, these simulations, and interacting with them in whatever way is most convenient, whatever is most appropriate for what you're doing. I know there's no way that I'm going to get my mother into some kind of extended reality device. That's just not going to happen. But once you've got these representations, once they're shared appropriately, then you can interact with them. You can have a variety of different portals into that experience. It can be a traditional screen, it can be a tablet, it can be a phone, or it can be a specialized device for XR, for VR, for mixed reality, AR, whatever it is. Now, how is this vision going to come to reality? It's not going to be overnight, but what is it that's going to enable it? We see a variety of underlying technologies that need to come together to create what we think of as the true 3D web, the 3D web that we want. And it's essentially the next evolution in all of our web technologies. But it's going to be so different that it's going to take some revolutionary steps. But what do we need to do? First, we need a way to describe scenes that is open, or an open standard, that's extensible, because there's no way we're going to start off knowing everything we want to represent about 3D virtual worlds. And it has to be something which we can distribute effectively and that can connect up to all the available open source technologies. Now, you're probably aware that there have been a lot of efforts to bring 3D into our existing 2D web. I see enough gray hairs here that there are probably a lot of people that remember Vermal way back in 1994. Since that time, we've had X3D, we've had GLTF, WebGL, WebXR, WebGPU. And these have been somewhat successful. You know, we do have ways of putting 3D into the 2D web now, but they haven't really revolutionized things. They haven't taken over. And why is that? Well, we think that there's actually, they're actually taking a short-term practical approach, but not the approach that's going to take us to the long-term goal we want to get to. And that's because 3D is fundamentally a lot harder than 2D. And adding 3D into 2D is not the right approach. What you really want to do is ask the question, what's the right solution for 3D, and include 2D into that. So we believe that there are about 4 different dimensions where we need to approach things differently. The first thing is the foundation of this 3D web, or the foundation of this metaverse. It needs to be a 3D representation. We're not going to take HTML, modify it slightly, stick in a few little tags for 3D items, and get to where we want to get to. We need a different underlying fundamental representation for the 3D virtual worlds. Secondly, whatever that representation is, it needs to be incremental. What do I mean? Well, if I send you a bunch of HTML that's describing some 2D website, some web page, and then I want to change it completely, I need to essentially resend the entire HTML. There's no way, there's no protocol for saying, I want to make this little incremental modification. And that works in 2D. If I have a web page that I can send to you, you know, in a small fraction of a second, if it changes and I resend the whole thing, that works fine. But if we want to share virtual worlds, which are described by hundreds of megabytes or even gigabytes of information, then there's no way I can resend it when something changes. We need to just keep track of what the changes are and send only those. Third, we need to take advantage of powerful hardware. The web standards committees very appropriately are trying to make sure that whatever you put on our existing web can be viewed by whatever devices we have available. And it's great. You put something up, you know everybody can see it, but this demands that we use the least common denominator approach. And insisting that everything you put on the web is viewable by an 8-year-old low-end phone is not going to get us to this promised land of the metaverse. So we think that instead we should target much higher hardware capabilities, and where necessary, stream them to less powerful devices. The fourth point where we think that we need to make a change from the kinds of efforts people have been doing in the past is to make sure that whatever this 3D world is that we're describing is flexible at all times. Now, in the past, particularly the game community has taken a lot of optimization steps. They have restricted what can happen inside a virtual world, optimized it like crazy, baked it out, so only a very limited number of things can happen. That's been great, made a lot of sense for the purposes for which it was designed. But to get to the true metaverse that we're looking for, we're going to have to build it on something that's much more flexible, because it's not simply a game experience. We want to have all those kinds of applications that I mentioned at the very beginning. But what is that representation that we all need to build on to get to this promised land of the true 3D web or the metaverse? We think it already exists, and it's something called USD, Universal Scene Description. It's a representation that was developed over decades at Pixar, and they were nice enough to open source it, which was really, really a fantastic gesture. Some people think of it as a file format. Well, yes, there is a way to take this data and serialize it out to a bunch of files, but that's not fundamentally what it is. What it is a scene description, an in-memory representation of everything that you care about in a virtual world, and APIs for creating that representation, for modifying that representation, and for querying it so that you can do whatever you want to experience to modify this virtual world. At its base, it's built out of properties and values. So those properties and values are combined together into groups, which are called schemas. So for example, if you have a mesh, you'd have a collection of properties. One property would be the points in the mesh. Another would be how many mesh points form each polygon, and then what is the connectivity. Out of the box, it comes with some schemas, but you can add arbitrary schemas. You can add additional data wherever that's appropriate. And the whole system is designed to allow collaboration of a variety of people working on the same data set. As I mentioned, it comes with the kinds of schemas that are necessary for Pixar's purposes to make feature films. That includes geometry, that includes cameras, lights, it includes character rigs, it includes materials, it includes the relationships among these things. It has a very, very powerful set of capabilities for inheritance, for specializing things, for doing overrides, for instancing. You can make a copy, you can change certain properties. It scales to very large data sets. It allows for lazy loading. And it allows you to have different versions of things, different variants, depending on the needs at the particular moment. Are you going to, are you very close to it? Do you need it all the geometric complexity? Are you going to simulate it? Do you need all of its physical data? All of that can be handled separately in different levels of detail, different representations for different purposes. Probably the most interesting and unusual aspect of USD as a representation of a virtual world is that it's fundamentally based on layers. Layers are in some ways similar to the idea of layers in Photoshop. You take all the layers together to get the full description of the scene. And what's interesting is that each layer has new properties, new values, and they're ranked in strength. So the strongest layer will win out in this composition. What it means is that different people, different services can read and write off of different layers of the full information in the scene. And depending on the power of the layers, they can override each other in a very interesting and powerful way. So what you see here is an example of a factory. There's one stack of layers that are describing the robots in the factory, their sensor data, their electrical information could be on separate layers. it's not forced to be, but it's allowed to be. And then the data in these layers can be turned on and off, just like a Photoshop layer that you can activate and deactivate. And then they can be updates, can be in a separate layer so that you can keep all this separate, and they can be written or read independently. Here's another example of characters, layers used on characters. We have the base mesh of the character created in a tool called ZBrush. We have props added in 3D Studio Max. We have lighting added in a tool from NVIDIA called Omniverse Create. We have materials added in Adobe Substance, all of those on separate layers, again, which can be turned on or turned off independently. So we've taken USD and we've added a lot of different things to it, but the one I want to point out right now is that we've made it incremental. So we have an additional library. If you make use of the library, then you can use the USD APIs to make any changes you want to this virtual world. You can add data, you can modify things, you can change positions or materials or geometry, anything you want. And this library keeps track of everything that's changed. And then at some point, when you want to tell the rest of the world about that, it can create a message consisting only of the changes that you can then send over to somebody else, and they can use that to update their representation so that now they're sharing the same world that you just created. There's a variety of other pieces of USD that we're adding to bring us towards the requirements to create this true metaverse. One thing is that USD is originally designed was mostly used by Pixar to evaluate things that they had created. It wasn't used for high-speed interactivity, so we're trying to fix some of that. We've actually built our autonomous car simulator on top of USD, and it works in hard real time. So we have essentially VR for the car. We simulate all the sensors, and that state of the world goes directly into the car autonomous driving brain as if it was really out in the real world. And that all works in hard real time. A gap in USD until we did the additional work was in materials. So USD supports a lot of different possibilities here. We've open sourced our solution for materials we call the material definition language to make it possible for anybody to put very, very high-end materials into a USD-based virtual world. Another thing that is a key piece of the puzzle is proceduralism. You have this world, you want it to change, to simulate, to give you interesting behaviors. We have a solution for that we're developing. It's something we call OmniGraph. And then last thing here is that we've open sourced our rigid body simulation library on top of this whole infrastructure, so that if in USD you specify the physical properties, you can then simulate the rigid body dynamics of what will happen. So first I'm going to show you an example of physics in USD. We developed a schema in cooperation with Pixar and with Apple to describe the relevant physical properties, things like moments of inertia, coefficients of restitution, collision geometry, things like that. And here you see it being used actually for layout purposes. So this is one of the applications that we've put together based on all this infrastructure. And you can pull things around live, simulate their collisions, interactions with each other. And very often you want physics just to lay things out. And so this lets you set things in proper positions for that. Here's a view of MDL, our material definition language. So what's special about it is that we've taken steps to make sure that it's always going to be physically accurate. So traditionally in computer graphics, you have some procedural shader. It looks at the light coming in, it tells you what light's going out, but there's absolutely no guarantee that the thing is physically plausible. It can, it's very frequent to have shaders which actually create energy. So in MDL, we've taken care to separate out the patterning on the object of its various different properties from the way that it reflects light. And the reflection of light has to be energy conserving. So together, this guarantees you something that can be arbitrarily high quality, but guaranteed to be physically plausible. And also the separation between the patterning and the reflection of light allows us to take something which is described by a very complex procedure and distill it down into something which is approximate and faster where it needs to be. So how do we combine all these technologies together? At the center is a database server, something we've built we call Nucleus. And it operates by publish subscribe. So basically, anybody can have a representation of the world in USD. They publish it, they publish changes. Anybody who subscribes to that stream of changes can then be synchronized to that virtual world. On the left, you see a variety of popular 3D content creation applications. Maya, Autodesk, Blender, Unreal, Revit, Substance, Rhino, SketchUp. The list is growing every day. And we have created plugins, connectors that allow them to synchronize through the Nucleus server. And in the end, the result is something we sometimes describe as Google Docs for 3D. So now everybody's speaking the same language. That same language is USD, it's incremental, it's live. Whatever people do can be seen across all those applications. You want to see the result of it. So we've built some special applications ourselves, Omniverse Create, Omniverse View. And we've put in a renderer, which is actually extraordinary. It completely takes advantage of every hardware feature in GPUs to give you ray traced quality, which was just unimaginable a few years ago. And I'll show you some examples of that. And that rendering technology can drive whatever device you want. It can be in a workstation on a traditional screen. It can be in virtual reality. It can be augmented reality. It can stream into a web browser. And you can get the universal accessibility by streaming it from a powerful device to whatever it is that you actually have in your hands and need to use. And in addition to this sort of input editing and portal into it, you can connect any microservice you want to this database server. And that microservice could do anything. It could look at the world, create some kind of behavior that's based on a simulation. It could be computational fluid dynamics. It could be rigid body dynamics, which I've just shown you. It could be a factory simulation. It could be any of those things. And essentially, it connects up to the database server, can ingest a description, full description of the world, modify it in any way. As it modifies it, it's seen by everybody who's connected. So how do we connect up those applications? Most of the things that are interesting that already exist are not based on USD. And so what we've done is we've built plugins for these applications. And the plugin has a copy of the USD library. So what we do is we essentially mirror between the USD library and whatever the representation inside that application is of the 3D virtual world. So you're in your application, you hit some buttons, something's changed. Generally speaking, the application will have a notification mechanism. We intercept those notifications. Inside of the plugin, we make the same modifications to the USD library. And vice versa. If something happens from the outside world, delivered by the Nucleus server through the publish subscribe mechanism, we make that modification to the USD library and then make the corresponding changes to the internal scene graph of whatever the application is. This is an example of the rendering that our RTX renderer is able to do. It's really pretty special. Because of the abilities of our hardware to do literally billions of ray triangle intersections, we actually do all of our rendering with ray tracing. So we don't, a lot of people do first bounce in rendering using rasterization and then trace rays after that. We don't do that. We actually ray trace the whole thing. Why does that matter? The main reason it matters is that it means that our render time is now independent of the scene complexity. You have to read in the whole scene, put it into spatial data structures in order to render it. You pay for everything in the scene when you load it. But per frame, as you're experiencing this virtual world, you don't have to touch every geometric primitive. If it doesn't move and it's in the spatial data structure, you only pay for it if the ray actually hits it. And that means that the rendering time is largely independent of the geometric complexity, which allows you to take the real models that people use in design, for example, put them into this situation, this environment, without ever having to decimate it to the simplicity that's required in most other systems. So this is there's some examples showing you the kind of lighting effects that you get with our path tracer. And now I'm going to show you that renderer operating in real time, connecting up to several other different applications. So in the upper left, we have Unreal. On the left in the center, we have Adobe Substance. At the bottom, we have Maya. We have three different people using those applications on the same virtual world. At the bottom, the Maya user is going to be doing some modeling. The Substance user is going to be applying some textures, and the Unreal user is going to be moving some things around, doing some layout. And you'll see the result through our renderer on the right in an application we call Omniverse Create. So here you see it in action. Sped up slightly, but you see the live updates going across all these applications. As these different users with their different talents, their different purposes, can all collaborate to build a single 3D world. Here's another example. This is from architecture, engineering, construction.
Kevin, in the bottom left, is loading the landscape from 3ds Max and aligns it to the Revit building. Dave, in the bottom right, adds windows on the building in Revit with instant results in Omniverse View. Jay, in the upper left, adds the auditorium interior variants using 3ds Max. While Jay in the upper left toggles ceiling dome variants in 3ds Max, Dave is testing results by changing the time of day.
So now I'll show you an example of physics happening in one of these sort of virtual reality kind of worlds. So this is combining the technologies that I described before, USD to represent the world, the physics schema to represent all the physical properties, our rigid body simulator running in real time. We have somebody in VR who's able to interact with all of this. And it's all running live interactively across a number of different applications. Collisions here are done with convex decompositions. Here he gets to play with the horse. And the ability to connect together this physical simulation with a good visual simulation is something pretty new, but something that's gonna take over, I think, before very long. Here it's all put together into a sort of a game demo that shows off the capabilities together. So you'll see very high-end rendering, live, everything live, connected with physical simulation of rigid bodies. And this is all running on just a single GPU. As I said, we believe that we need to target a very high level of quality. And we're doing that across whatever range of devices you may have, instead of targeting the least common denominator. And here we'll see that approach in a simulation of the lunar lander. We have this astronaut being driven by an actor, well, actually an NVIDIA engineer. We have a camera using an AI pose detection algorithm. That pose is being used to drive the character. We're doing the full lighting, real time. And then we have somebody with an iPad viewing the scene. We actually use ARKit to compute the point of view of the tablet, and we stream that back to the Nucleus server so that any client can use that for rendering. You probably saw quickly there's somebody else who's using a desktop application who spun the flag around. Everybody's in the same virtual world. Here's another example. I hope. Yeah. Here we have two groups of people. One group in St. Louis, one in Santa Clara, California. We have two actors. They're in inertial motion capture suits. So as they move around, the outputs of their motion capture suits are fed into the Nucleus server. And then we have a virtual camera operator, again holding an iPad. And there you see them thousands of miles away from each other, but inhabiting the same virtual world, using this infrastructure, using USD, using the database server. And here's another very important application, which is, as I mentioned early on, that we have AIs that are going to learn in a virtual world, right? Well, what are they going to learn? They need training data from some source. And one source of training data is to use the real world. You can take videos, you can hire a lot of people to laboriously label each pixel of each of those images with whatever it actually represents, so that you can train an algorithm to recognize things appropriately. Or you can, if you have a good enough simulation of reality, you can train inside of a virtual world. And what does that mean? Well, you generate the scene, you generate the world synthetically. Now you know the labeling. You know exactly what each pixel is showing you. But if you do that, you need to create sufficient variety for the AI so it's not confused and doesn't overfit and believe that everything of every instance of this particular tool has this particular color or would be confused by different lighting. And so what we do is, in this virtual world, we generate a variety of different variations. We run through the scene description and we randomize it. Domain randomization it's called. So this video will show you how we can train a robot to run around inside of a factory by generating a vast number of different randomized possibilities, each of which is labeled precisely by the data that was used to create it, without having to have any human tagging. And this kind of training of AIs has been very, very effective. You also probably want to supplement it with real world data, but as the simulation of the environment, the intersections, the physics of the light gets better and better and better, this becomes a fully viable way to supplement, or in some cases even replace, the data from the real world. And similarly for robots, robot AIs need to figure out how they're going to accomplish tasks in the virtual world. And this video shows us training some of these robots, thousands of copies of them simultaneously, inside of the same virtual worlds that I've been describing. Running simulators, letting the robots try things, noting their failures, using those failures in reinforcement learning to adjust the weights on their neural networks, repeating and repeating until they accomplish the tasks effectively. So these virtual worlds, they're for us, they're for simulators so that we can figure out and make correct decisions. They're for AIs to train themselves and become part of our physical worlds and also become parts of our virtual worlds. One of the big applications of the 3D web and the metaverse is something called digital twins. And the idea here is that we want to be able to create virtual versions of the real world so that we can make the right kind, so we can understand what's happening in the real world, make the right kinds of decisions, and figure out how to make the physical world more efficient. In the physical world, you have, for example, real factories. They operate with real sensors. They have motor controllers. They have people running around them. Then you have the virtual world. Well, if you want to use the virtual world to see what's going on in the real world, you're going to need to match that. So we're building real-time synchronization between the two. Those sensors, they report IoT data. We bring that data over into the virtual world so that it evolves, it moves in synchronization with the physical world. And then in the virtual world, we're able to simulate the physics. We're able to train the AIs. We're able to render it, make it as beautiful as we can. When you get this link between the virtual and the physical, you get to do some extraordinary things. First, I'll show you this video of a collaboration we've done with BMW, creating a virtual twin of their factory. And apologies for some of that being a little bit too much in the marketing direction, but you should be able to see some of the things we can do here.
BMW has continued building on the momentum of their Factory of the Future initiative we showed you earlier this year. On average, they produce one new vehicle every minute, expanding the initiative to now include digital twin projects at 3 additional factories, which total more than 6 million square meters. Meeting BMW's demands for continuous improvement and innovation requires simulation of complex production scenarios to speed output, increase agility, and optimize efficiency everywhere. NVIDIA Omniverse introduces new simulation capabilities everywhere BMW needs to make critical decisions and introduce automation. BMW and their partners have also been connecting new users and tools to expand the Omniverse ecosystem. Spanning every aspect of the BMW Factory of the Future, Omniverse allows BMW to collaborate and simulate from the entire plant level down to comprehensive engineering detail.
So you see that with ray tracing, we can handle the full complexity of the CAD models, even in those very, very, very complex environments. So once you combine the virtual world and the real world, you get to do some extraordinary things. One thing you can do is you can teleport. So if you're in a real BMW factory and you want to get from one end to the other, it could easily take you 20, 30 minutes. These factories are just vast. But with a digital twin, you can be wherever you want instantly. You can teleport. You suddenly become superhuman. And not only can you teleport in space, you can teleport in time. You want to know what happened last Thursday. You want to be there as the plant was operating when something untoward happened. Figure out what caused that fall. You just roll back the time, and there you are. You can see what was going on. You do the same thing into the future. You have the right kind of simulation. You have an order flow that's coming in. You want to know if the factory is going to be used efficiently. You run that simulation. Oh, you don't like it. Okay, now it's time to modify that feature. So you want to explore alternative realities. This virtual world doesn't have a single expression. Each one of those layers that I described to you in USD, they can be changed to show you different possible outcomes. You can explore them and make the best use you can out of your facilities. So here I'm going to show you a bunch of different examples of this in action. Here's the BMW factory again. Simulation of robots. Simulation of the people operating the factory. This is our autonomous driving simulator, showing you the sensors for different parts of the car, applications, architecture, construction. Over there. So our goal is to build all of this on open standards and open and extensible standards. So we welcome all the different communities, including geometric algebra, to help us understand how these representations of the world should be expanded, how we can have elements of what's important to all these different communities, to embed these into new USD schemas, to make them understood across a wide variety of tools so that they can interact with all the technologies that I just described. We think this is the way that we get to the promise of the true 3D web and the metaverse. So I'll finish showing you some a final video here, and then we'll have questions of some of the capabilities that Omniverse brings together with all the different tools that are connected to it.